All right, welcome back. In the previous recording, I described, discussed, and mentioned to you the concept of the electric field. Sorry, I'm fiddling with something here. And I described the electric field. I gave you two major properties about it. One was that the electric field is a creation of an electric source charge, and there's a subtlety there, and I'll talk about that in a little bit. But in any case, so we have two charges that manage to experience forces, one from the other, and the question was, how does the one charge experience the force from the other when the two don't touch each other? And the answer that I proposed was a model of something that I call the electric field, and I described the electric field, used the analogy with water on a lake, so I on the shore could affect something that's sitting out in the water by pushing on the water, and then the water would transport my influence from me to the boat. And so in that sense, then that I can apply a force on the boat indirectly using the water as an intermediate mechanism for transporting my force to the boat. Similarly, we imagine a couple of charges. One creates this electric field. The electric field is the mechanism that transports the electric influence, the electric force, from the source charge to the other charge, which I labeled and named the test charge. Okay, the source of the force and the thing that experiences or tests the force. What I want to do now is give you just sort of a hand-wavy kind of sense of what is in my head when I talk about an electric field of a source charge. What does it look like? What do I want you to imagine? And so what I'm going to do is draw you a few pictures of what the electric field we imagine looks like of various types of source charges. Okay. Now, I want to make it clear in advance that I don't expect or even particularly need you to understand why the fields look the way they're going to look. I'll talk a little bit about it as I do it, and I'll point at a few things, but it's not my purpose in this recording to make you experts on why the field diagrams are going to look the way they're going to look. More, I want you to see what can fields look like, how complicated can they get, and what sort of things do we have to think about in trying to picture such a field. Okay, so we'll start with perhaps the simplest one, which is a positive single point charge, like a proton or like the nucleus of pretty much any atom. The nucleus of an atom, even with dozens of protons in it, is still so physically small that we can very, very reasonably and almost perfectly correctly think of it as just a single point object. It isn't really, but as long as we don't get too close to the nucleus, then it's perfectly great to treat it as a point charge. So that said, that last bit was only because I don't want you to think every time I talk about a point charge that I'm talking about a proton. That's not the case. Okay, it can be any collection of charges of any amount of coulombs, as long as it's physically small compared to how far away you are from it. Okay, right. So that said, let's do some field examples here. Okay, so our first example would be a positive point charge. All right, so we have our positive charge Q here, and its field is going to be uniform around it, uniform in space, and as I will explain, or start to explain anyway, in just a moment, the field is actually a so-called vector field, meaning that it has a direction. Okay, so I'm going to include that information in my drawing. Again, without any particular explanation of why it looks like this, not yet anyway, this is typically what we draw when we draw the field of a point charge. Now, in reality, this is nowhere near complete. what you are supposed to imagine is that there are these straight blue lines radiating outward from filling every single part of the board. But of course, if I did that, all I'd end up is drawing you a big blue circle, that's completely filled in, and that wouldn't be useful. I could, if I wanted to, draw more of these so-called electric field lines. Okay, and the more I drew, the more realistic this field would look like, this field diagram would look like. But on the other hand, the more crowded the lines become, the less useful it is. And so usually, for a single point charge anyway, we tend to stop at just 8 lines. The goal, and this is getting a little ahead of ourselves, but that's all right. The goal of making a field line diagram is to give the person looking at your diagram a clear idea of what the field looks like everywhere in space. And so anywhere where the field, and you'll see examples of this in a moment, anywhere where the field changes rapidly from place to place to place, we have to draw more lines so that the person looking at our diagram can see what's going on with the field. But for positive point charge, it turns out that the field is pretty boring. It's about as boring as it gets. The bunch of straight lines, they're all start at the point charge, start at the source charge, and they point outward, as it turns out. So I mentioned that these things are vectors, and they are. And so we put arrows on them because they're vectors, and they point a certain direction. And the direction of these electric field vectors for a positive charge, positive point charge, they point radially away from the source charge, radially outward. Why radially outward? That'll be the next recording. Partly it's just by definition, but not entirely. Okay. But whatever. Without further explanation, this is what we kind of picture, what I want you to picture when we talk about the field of a point charge, of a positive point charge. Okay, nice uniform bunch of lines all radiating outward from the source. The field of a negative charge is our next example, and is perhaps a negative point charge. Perhaps it won't stun you to learn that the field looks very similar to the field of a positive point charge. And in fact, you can probably guess what it's going to look like. Indeed, you should probably pause the recording at this moment and predict what I'm going to draw if you don't already know. And hopefully you did that. Okay, so we have a negative source charge here. And the answer is the electric field of a negative point charge looks exactly the same as the field of a positive point charge, except it points in the opposite direction. Again, there's meaning and importance to the direction that these things point. And I'm getting a little sloppy here. They should all, these electric field lines should all should all terminate on the charge itself, on the source charge. All right, so there's that. Now we'll combine the two. And to be honest with you, it's been a while So I don't actually remember whether I mentioned this in the previous recording, but I have to go over here and get something. Hang on. Sorry, I need some colors I didn't bring with me. Okay, so this third one, again, I don't remember if I've told you about this particular thing or not, but anyway, this is going to be the field of a dipole. Just in case I haven't said it before, so a dipole is actually a construct of two charges, 2-point charges, one positive, one negative, and almost always when you talk about a dipole, the two charges have the same number of coulombs, the same magnitude of charge. And so we'll have a, doesn't matter where you put them, positive charge on one side, negative charge on the other. And this time I'm going to use a neutral color to represent the field because the total field is going to be a mixture of the field of the positive charge and the field of the negative. Now, again, I'm not in this recording going to justify the diagram that I'm going to make, except to say that the total electric field that exists everywhere in space is the result of adding the electric field of the positive charge to the electric field of the negative charge at each point in space. So you go here and you say, okay, right here the positive electric field would do this, but at the same point the negative electric field would do something else, and you add those two together to get the total field, and the total field is what you draw. In a later recording, we'll go through that in more detail, but for now, the result ends up being again, what do I want you to picture when I say, oh, the electric field of a dipole in this case? Okay. And so it looks basically like this. There's a few features that I want you to notice. The field lines are getting increasingly farther and farther apart as you get farther and farther away from the source charges. That's important. Furthermore, as was true in the previous two diagrams, the field lines start and stop on the charges, or the other possibility, and we'll talk about this more, but just so you see it here, either the electric field lines start and stop on a charge, or they go out to infinity, okay? Either positive infinity or negative infinity. And by that I mean you in your imagination would extend the electric field lines till they're infinitely far away from you. In practice, we go about that far. And then finally, pardon me, as far as the directions are concerned, these are still vectors. We still have to worry about that. And the same rule applies for all fields as it does for the individual fields of the point charges, which is the field lines point toward negative charges and point away from positive charges. And so here we're pointing toward the negative charge, and conveniently away from the positive charge. Okay, so that would be a pretty nice electric field diagram for a dipole. At the end of the day, what's going to happen is that these drawings are going to, believe it or not, actually help us answer questions, solve problems regarding electric fields and electric forces. I am now going to stretch my drawing skills to their absolute limit, and I expect I'm going to fail spectacularly, but I'm going to try anyway, because you never improve yourself if you don't try, right? Get out of your comfort zone. So I'm going to attempt, get this, to make a three-dimensional, a two-dimensional projection of a three-dimensional image. So wish me luck here. Okay, so there I have my positive charge, and I'm going to do this in kind of a perspective drawing here. And there's my negative charge, and my field lines. In this case, again, I need some more colors. I'll be right back. Okay. So I'm going to basically, I'm actually just trying to copy this image that I see on my tablet here. And kind of like that. And maybe a few that go like that out into space somewhere. And here's another one, another set that. And what I'm trying to communicate here, however well I'm succeeding, I'm not sure, but what I'm trying to portray here is that the field is a three-dimensional phenomenon. This is important. It's not easy to see, and I'm not sure I'm at all pleased with this diagram, but in any case, no point in overdoing anything. The field vector, field lines, field vectors here, field lines really, project out of the board as well as on the board, and they also project behind the board. So it's a three-dimensional phenomenon. So what I'm trying to get you to imagine, trying to get you to picture, is this field exists throughout three-dimensional space, not just two-dimensional. And what the heck? There's no point in not doing this. Let me show you the picture that I'm actually trying to create there for you. Okay. So that's. I have now blown up my head as regarding my ability to draw. All right, so this is the field of a dipole. Again, very important concept that electric fields, all electric fields, are three-dimensional. Okay. Just a couple more examples of what field diagrams can look like. You might remember the smallest possible charge. I mentioned that, the so-called quantum of charge. In the SI system, it's 1.602 times 10 to the negative 19 coulombs. And no matter how you slice it, that is an awfully small number. And what we will end up doing very soon is we're going to stop thinking about, caring about, and calculating with just one or two individual point charges, but we're going to end up working with hundreds, thousands, trillions of charges, and there's no hope in the world that we would try to calculate them one charge at a time. So what we're going to do is start imagining some sort of an electrical paste or electrical jelly or continuous electrical fluid, basically a continuous charge distribution. We'll talk about it more again another time, but the reason I bring it up at this point is I want you to now imagine a piece of metal, a piece of aluminum foil, or a thin aluminum plate, or anything else like that. And by some mechanism or other, maybe rubbing the plastic rod and then touching it to the metal plate or whatever, I managed to sorry, I keep needing pens, and they keep being on the other side of the room. Anyway, somehow or other, I managed to add and deposit a whole bunch of, that is to say, a vast, huge number of electric charges, let's say positive, on no, let's say negative, and a whole bunch of negative charges on the surface of this. And so what's going to happen is that I'm going to imagine that the electric charge, this negative electric charge, is distributed uniformly over the surface of this metal plate, something we'll talk about later in the quarter. Right now, I'm only interested in the field that it creates, but imagine, if you will, just sort of a continuous distribution of negative charge, which I can't draw from that angle. Continuous, uniform distribution of negative charge living on the surface of this metal plate. And then, because why not, let's imagine a positive charge nearby it, and this actually will have real physical applications at some point. Put it over here a little further. And then what will the field of this thing look like? Again, I'm going to draw it in a neutral color because we've got a positive field and a negative field, but the rule is the same. We're going to, the two rules, the total field at any point in space is the sum, the superposition. What was that word? Superposition. Superposition means to add them together. The total electric field everywhere is the superposition, the vector sum, of the electric field of the negative plate plus the electric field of this positive point charge. Without justifying it, I'm simply going to draw it, and it will look like this. Okay, and again, the arrows on the field vectors need to point away from positive charges and toward negative charges. And so we'll put them on like that. Okay, and just a couple of things that I want you to notice about this particular one. On the side, when we're far away from the negative plate, the field lines look an awful lot like the field lines that I drew for the field of just a positive point charge, which maybe is not surprising because, after all, although over here the negative plate definitely should have an effect on what the total field is right here, we're pretty far away from the field. I'm sorry, from the negative plate. We're pretty far away from the negative plate, and so whatever influence it's going to have on the total field here, it seems reasonable to think that it's going to be fairly small because we're pretty far away from it. Okay, and the farther we get away from the negative plate, the less its influence should become. So it seems reasonable that the field over here should be pretty much the field of a positive charge. Whereas, on the other hand, when you're close to the negative plate, the reverse argument is true. The field at points in space very close to the negative plate should be strongly dominated by whatever field is created by the negative plate, and the effect of the positive point charge should be pretty small much, much smaller than the field of the negative plate itself when we're close to the negative plate. And at intermediate locations, the two fields have more or less equal contributions to the total field. So yeah, so that's what it looks like. The other thing I want you to notice is that for this uniform distribution of charge on the surface of this metal plate, as long as you stay close to very close to the plate, the field lines are pretty much perpendicular to the surface of that plate. And in fact, my last example will take this to the extreme. And once again, I will have a plate with a more or less, no, not more or less, a completely uniform distribution of negative charge on it. No, let me not do that. So negative charge over there. And then over here, I'm going to have another, and I'll assume just for simplicity, physically identical metal plate, but through some mechanism or other, and we don't have to care how it happened, we managed to deposit a uniform distribution of positive charge. Now we will see this. This is a real thing that we're going to care about. If you care, it's something called a capacitor. In any case, the electric field of this thing, as long as you stay away from, well, I'll just draw it. Sorry, I'm messing myself up a little bit. And I do need the plates to be reasonably identical so that my drawing can be reasonably easy to understand. All right, so let's try that again. Yeah. This one gets a little bit complicated near the edges, so you kind of have to be careful. There we go. And then for completeness, I guess I could do this. Most of the time, just so you know, we don't care about you go like this. We don't care about the field at the ends. But in any case, and once again, the field vectors are going to point towards negative charges and away from positives. Okay. And with some similarities to what you saw in the previous example, in the regions close to the plates, the field vectors are everywhere perpendicular to the surface of the plates. And in fact, because I have two plates here now rather than just one plus a point charge, not only is the field perpendicular close to the plates, but as long as you stay away from the edges, the ends of these metal plates, then the field is actually nice and parallel everywhere. A very nice uniform field. This thing, as I said, is called a capacitor, and it's important and useful because this is a mechanism for creating a nice, uniform, easy to create, easy to manipulate, and easy to calculate electric field Very, very simple thing. Just two bits of identical metal, puts a bunch of charge on one, a bunch an equal amount of put a bunch of positive charge on one, a bunch of negative charge on the other, same amount of negative and positive charge on the two plates. Put them close to each other, and boom, you got a nice uniform electric field. Once you have an electric field, then you can do any electric forces that you want, easy to calculate. Okay, so bottom line from this entire lecture. These are the sort of diagrams that you get when you do electric fields. This is what electric fields look like in space. And the hardest part about this entire course is trying to wrap your head around what in the world an electric field is. So this is our first crack at dealing with that issue. Okay, so fields are constructed from a bunch of curved lines. They're curved based on a whole bunch of things that we'll talk about, and they are vectors, meaning that they point in certain directions. So you got to put the arrowheads on them, and they can get pretty crazy looking. And so that's that. All right. So our next recording will talk about the mathematics of an electric field. How do you calculate it, and how does that calculation of the electric force relate to the calculation of the electric field, how does the calculation of the electric field relate to the calculation of the electric force that the field is causing? That'll be next.